Hi, everyone. My name is Sarah Kane, and I'm a rising sophomore in the College of Arts and Sciences. Thanks for stopping by my poster. Through Perm this summer, I had the privilege of working under the mentorship of Professor Boov Jain and in collaboration with Eli Whiston to look for exoplanets, which are planets outside our own solar system, orbiting a star other than the Sun. The search for exoplanets is invaluable because it helps us understand our own solar system, identify potentially habitable worlds, and just maybe bring us one step closer to knowing if there is life beyond Earth. Our goal was to look for exoplanets that are just a bit too small to find individually by combining the signals from many planets at a time to make one stronger signal. This project is especially exciting because these smaller worlds are more likely to be rocky planets, perhaps even Earth analogs. For our research, we were looking for periodic dips in the brightness of a star that could indicate that an exoplanet was passing in front of a star and obscuring some of its light. You can see our methods here. We began by making our own synthetic data, which fell into two categories: false positives with only noise, and true positives, which included both noise and inserted planetary transits. First, using the true positive data, we sought to test the limits of modern exoplanet detection techniques by varying system parameters such as orbital period and radius of the exoplanet, noise level, and so on. You can see our results from one such test in Figure 1, right here, which displays the power of an exoplanet detection as a function of orbital period and noise level in an Earth analog system. After testing the limits of typical detection techniques, we moved on to quantifying the difference between large groups of stars with and without exoplanets. To do so, we compared the true positive detection strength to the false positives with a statistical test to derive the probability that the two samples arose from the same overall distribution. After testing our simulated true positives against our false positives, we began using three categories of real data as our test sample. First, we tested a randomly selected sample of 1,000 stars, which did not differ significantly from the false positives. Next, we tested the data from stars with known exoplanets, and as expected, these data did differ significantly from our simulated false positives. Finally, we applied our technique to the objects of interest, which are stars that have been identified as potential planet hosts. As you can see here in Figure 2, the objects of interest differ significantly from the noise of our false positives in every period bin, but further research is needed to determine whether these differences arose from planetary transits or some other astrophysical source, which could also prove quite exciting. Eli and I have plans to continue that further research this fall with Professor Jane by using machine learning to identify potential exoplanet candidates. There certainly are more planets hiding in the data for researchers to find, and I look forward to seeking them out. My research this summer would not have been possible without the excellent mentorship of Professor Jane or the partnership of Eli Whiston. We also received invaluable expertise from Professor Colin Blake. I would like to thank the Valet Women's Science Research Fellowship for funding my research this summer, and the staff at the Center for Undergraduate Research for making the PERM experience so meaningful. Please feel free to contact me with any comments or questions regarding our research, and enjoy the expo. Thank you.